We can also form anhydrides from two carboxylic acids, or sometimes even from one molecule that's a diacid. And it's really the same sort of thing. Who has electrons? One of the hydroxide oxygens have electrons. Who wants them? A carbonyl is going to want them. So if I do this reaction, electron pair goes up onto the carbonyl oxygen. I can get an intermediate. Now when we look at leaving groups, if this electron pair comes back down right away, carboxylate here, or this carboxylic acid, would be a good leaving group. And we would just get back to the start. If we keep doing this enough, eventually what can happen is this OH over here can grab the proton, pushing this electron pair over here onto the oxygen to get rid of the positive charge, making a second intermediate, where now I have another very good leaving group, which would just be water. So now if the electron pair comes back down, water is my leaving group, and I form an acid anhydride plus water. In this example, we can use the Le Chatelier's principle to drive this reaction forward by the fact that we're making water as a byproduct. So if there's a way that we can remove water from the reaction, then we can drive this reaction forward, because once we get an anhydride, it won't be able to reverse. So even if the equilibrium lies mostly towards being two separate acid molecules, if we can take out one of the products, we can continually drive this reaction forward, even if it only makes a small amount at a time. And that's one of the things we've talked about in class before. One of the examples is you can use molecular sieves. Molecular sieves are those ceramic balls that have pores on them, and you can get the ones that have the exact pores on them that are the right size for a water molecule to fit in there. And the pores are hydrophilic, or the surface of the ceramic balls are hydrophilic, so they like water molecules. So every time a water is formed in a reaction, the molecular sieves will soak it up, and then this reaction can't reverse. And that's a great way to push a reaction forward like this. And the same can be done in trying to form esters from carboxylic acids. So if we have a carboxylic acid, and we're going to react it with some kind of an alcohol and some kind of an acid catalyst. So see if you can draw this mechanism out from the things that we've done before, and then come back and see how it worked. I understand that the who has electrons, who wants them is a little bit complicated in this reaction. Clearly the proton wants the electrons. Who has the electrons is a little bit harder question, as there are three different oxygens here in this reaction. However, what you hope to happen in the reaction is we want this alcohol to be the nucleophile to attack our carbonyl to make an ester. So to accomplish that, if we protonate our carbonyl first, that leads us in the direction of making the carbonyl more reactive to a neutral nucleophile. So now once our carbonyl is activated, now this weak nucleophile is strong enough to add, pushing the electron pair out onto oxygen to eliminate that positive charge. Right now, this alcohol, protonated alcohol over here, would be the best leaving group. But if we take one of these OHs and grab that proton, which eliminates the positive charge on the ether, now we have a good leaving group. So now the water can leave, leaving a carbocation behind. And then we can use that water or another water molecule to come along and deprotonate to get rid of our positive charge. So if I deprotonate this alcohol, this electron pair can come over here and reform a carbonyl, getting rid of the positive charge. And we get our final product, the ester. And in the end, H2O plus H is H3O plus. H plus and water. We have water as a byproduct, just like we did in the last reaction. So if there's a way that we can take water out during the reaction, then we can drive this reaction forward, again using Le Chatelier's principle. Because there isn't a lot of difference in stability between the alcohol and the water. So we can't use pKa's to drive this forward. In this case, we can use Le Chatelier's principle. There's a couple of ways to do it. As we talked about in the previous one, you can do it using molecular sieves. Another way is that water usually has a lower boiling point than carboxylic acid or a lot of esters, especially larger esters. Smaller esters would have a lower boiling point. And so sometimes you can just boil the water off the reaction Or you could boil off the ester off the reaction so that it can't reverse to reform the carboxylic acid and the alcohol that we started with.